In the previous videos, we explored Fourier series and its 11 properties for periodic signals. But here's a natural question. What about signals that are not periodic? Aperiodic signals, like a single rectangular pulse or a decaying exponential, don't repeat forever, so we can't directly apply Fourier series to them. In this video, we'll bridge that gap. We'll derive the continuous-time Fourier transform by starting from Fourier series and taking the period to infinity. By the end, you'll have the ft and inverse ft formulas that work for any aperiodic signal. Here's the key idea. Suppose we have an aperiodic signal x of t, maybe a pulse that exists only for a finite duration. We can artificially make it periodic by repeating copies every t seconds. This creates a periodic signal x tilde of t, defined as the sum from k equals negative infinity to positive infinity of x of t minus kt. Think of it as tiling x of t along the time axis. One period of x tilde is exactly our original x of t. Since x tilde is periodic with period t, we can apply Fourier series to it. The Fs coefficients are x tilde of k equals 1 over t times the integral over one period of x tilde of t times e to the minus jk 2 pi over tt dt. Now here's the crucial step. Since one period of x tilde is just x of t, and x of t is 0 outside that interval, we can extend the integration limits to negative infinity to positive infinity. So x tilde of k equals 1 over t times the integral from negative infinity to positive infinity of x of t e to the minus jk omega 0 t dt. Now let's extract something powerful from this expression. Multiply both sides by t. We get t times x tilde of k equals the integral from negative infinity to infinity of x of t e to the minus jk omega 0 t dt. The right side depends on the continuous variable omega, evaluated at discrete points omega equals k omega 0. So we define a new function. X of omega equals the integral from negative infinity to infinity of x of t e to the minus j omega t dt. This is the Fourier transform of the aperiodic signal x of t. Notice the key relationship. X of omega, evaluated at omega equals k omega 0, gives us t times the Fs coefficients of the periodic extension. In other words, the Fs coefficients are samples of x of omega divided by t. X tilde of k equals x of k omega 0 divided by t. Now let's derive the inverse transform. The Fourier series synthesis equation for x tilde is x tilde of t equals the sum over k of x tilde of k times e to the jk omega 0 t. Substituting x tilde of k equals x of k omega 0 over t, and using t equals 2 pi over omega 0, we get x tilde of t equals the sum over k of omega 0 over 2 pi times x of k omega 0 times e to the jk omega 0 t. Look carefully, this is a Riemann sum. As t goes to infinity, omega 0, which equals 2 pi over t, approaches 0. The discrete frequencies k omega 0 become the continuous variable omega, and the sum becomes an integral. In the limit, x tilde of t approaches x of t, and we obtain x of t equals 1 over 2 pi times the integral from negative infinity to infinity of x of omega e to the j omega t d omega. This is the inverse Fourier transform. Let's put it all together. For an aperiodic signal x of t, the Fourier transform pair is forward transform. X of omega equals the integral from minus infinity to infinity of x of t e to the minus j omega t dt. Inverse transform. X of t equals 1 over 2 pi times the integral from minus infinity to infinity of x of omega e to the plus j omega t d omega. Notice the beautiful near symmetry. Both are integrals of the same form, but with opposite exponent signs and a factor of 1 over 2 pi in the inverse. In general, we can define the pair with constants c1 and c2, where c1 times c2 must equal 1 over 2 pi. Our convention uses c1 equals 1 and c2 equals 1 over 2 pi. Another popular choice is the symmetric form, where both constants equal 1 over the square root of 2 pi. Regardless of convention, the Fourier transform extends frequency analysis from periodic signals to aperiodic signals. In the next video, we'll discuss convergence conditions and compute our first Fourier transform examples.